The universe is vast and complex. The chemical level of organization, the lowest level of structural organization, consists of atoms and molecules. These letters of the anatomical alphabet ultimately combine to form body organs and systems of astonishing size and complexity. In this video, we consider how atoms bond together to form molecules, and how atoms and molecules release or store energy in processes known as chemical reactions. So remember to like, share, and subscribe for more videos on anatomy and physiology. Chemistry is the science of the structure and interactions of matter. All living and non-living things consist of matter, which is anything that occupies space and has mass. Mass is the amount of matter in any object which does not change. Weight, the force of gravity acting on matter, does change. When objects are farther from Earth, the pull of gravity is weaker, and this is why the weight of an astronaut is close to zero in outer space. Matter exists in three states: solid, liquid, and gas. Solids, such as bones and teeth, are compact and have a definite shape and volume. Liquids, such as blood plasma, have a definite volume and assume the shape of their container. Gases, like oxygen and carbon dioxide, have neither a definite shape nor volume. All forms of matter, both living and non-living, are made up of a limited number of building blocks called chemical elements. Each element is a substance that cannot be split into a simpler substance by ordinary chemical means. Scientists now recognize 117 elements. Of these, 92 occur naturally on Earth. The rest have been produced from the natural elements using particle accelerators or nuclear reactors. Each element is designated by a chemical symbol, one or two letters of the element's name in English, Latin, or another language. Examples of chemical symbols are H for hydrogen, C for carbon, O for oxygen, N for nitrogen, Ca for calcium, and Na for sodium. 26 different chemical elements normally are present in your body. Just 4 elements, called the major elements, constitute about 96% of the body's mass: oxygen, carbon, hydrogen, and nitrogen. 8 others, the lesser elements, contribute 3.8% to the body's mass: calcium, phosphorus, potassium, sulfur, sodium, chlorine, magnesium, and iron. An additional 14 elements, the trace elements, are present in tiny amounts. Together, they account for the remaining 0.2% of the body's mass. Several trace elements have important functions in the body. For example, iodine is needed to make thyroid hormones. Each element is made up of atoms, the smallest units of matter that retain the properties and characteristics of the element. Dozens of different subatomic particles compose individual atoms. However, only 3 types of subatomic particles are important for understanding the chemical reactions in the human body. These are protons, neutrons, and electrons. The dense central core of an atom is its nucleus. Within the nucleus are positively charged protons and uncharged neutrons. The tiny, negatively charged electrons move about in a large space surrounding the nucleus. They do not follow a fixed path or orbit, but instead form a negatively charged cloud that envelops the nucleus. Even though their exact positions cannot be predicted, specific groups of electrons are most likely to move about within certain regions around the nucleus. These regions, called electron shells, are depicted as simple circles around the nucleus. Because each electron shell can hold a specific number of electrons, the electron shell model best conveys this aspect of atomic structure. The number of electrons in an atom of an element always equals the number of protons. Because each electron and proton carries one charge, the negatively charged electrons and the positively charged protons balance each other. Thus, each atom is electrically neutral. Its total charge is 0. The number of protons in the nucleus of an atom is an atom's atomic number. For example, oxygen has an atomic number of 8 because its nucleus has 8 protons, and sodium has an atomic number of 11 because its nucleus has 11 protons. The mass number of an atom is the sum of its protons and neutrons. Because sodium has 11 protons and 12 neutrons, its mass number is 23. Isotopes are atoms of an element that have different numbers of neutrons and therefore different mass numbers. In a sample of oxygen, for example, most atoms have 8 neutrons, and a few have 9 or 10, but all have 8 protons and 8 electrons. Most isotopes are stable, which means that their nuclear structure does not change over time. Certain isotopes, called radioactive isotopes, are unstable because their nuclei decays into a stable configuration. The half-life of an isotope is the time required for half of the radioactive atoms in a sample of that isotope to decay into a more stable form. An ion is an atom that has a positive or negative charge because it has unequal numbers of protons and electrons. Ionization is the process of giving up or gaining electrons. An ion of an atom is symbolized by writing its chemical symbol followed by the number of its positive or negative charges. When two or more atoms share electrons, the resulting combination is called a molecule. A molecular formula indicates the elements and the number of atoms of each element that make up a molecule. A molecule may consist of two atoms of the same kind, such as an oxygen molecule. Two or more different kinds of atoms may also form a molecule, as in a water molecule. In water, one atom of oxygen shares electrons with two atoms of hydrogen. A compound is a substance that contains atoms of two or more different elements. Most of the atoms in the body are joined into compounds. Water and sodium chloride, common table salt, are compounds. However, a molecule of oxygen is not a compound because it consists of atoms of only one element. The forces that hold together the atoms of a molecule or a compound are chemical bonds. The likelihood that an atom will form a chemical bond with another atom depends on the number of electrons in its outermost shell, also called the valence shell. An atom with a valence shell holding 8 electrons is chemically stable, which means it is unlikely to form chemical bonds with other atoms. When atoms lose or gain one or more valence electrons, ions are formed. Positively and negatively charged ions are attracted to one another as opposites attract. The force of attraction that holds together ions with opposite charges is an ionic bond. An ionic compound that breaks apart into positive and negative ions in solution is called an electrolyte. Most ions in the body are dissolved in body fluids as electrolytes, so named because their solutions can conduct an electric current. When a covalent bond forms, two or more atoms share electrons rather than gaining or losing them. Atoms form a covalently bonded molecule by sharing 1, 2, or 3 pairs of valence electrons. The larger the number of electron pairs shared between two atoms, the stronger the covalent bond. They are the most common chemical bonds in the body, and the compounds that result from them form most of the body's structures. A chemical reaction occurs when new bonds form or old bonds break between atoms. Chemical reactions are the foundation of all life processes. The starting substances are known as the reactants. The ending substances are the products. The arrow in the figure indicates the direction in which the reaction proceeds. In a chemical reaction, the total mass of the reactants equals the total mass of the products. Thus, the number of atoms of each element is the same before and after the reaction. However, because the atoms are rearranged, the reactants and products have different chemical properties. Through thousands of different chemical reactions, body structures are built and body functions are carried out. The term metabolism refers to all the chemical reactions occurring in the body. Each chemical reaction involves energy changes. Energy is the capacity to do work. Two principal forms of energy are potential energy, energy stored by matter due to its position, and kinetic energy, the energy associated with matter in motion. Chemical energy is a form of potential energy that is stored in the bonds of compounds and molecules. The total amount of energy present at the beginning and end of a chemical reaction is the same. Although energy can be neither created nor destroyed, it may be converted from one form to another. This principle is known as the law of conservation of energy. Chemical bonds represent stored chemical energy, and chemical reactions occur when new bonds are formed or old bonds are broken between atoms. The overall reaction may either release energy or absorb energy. Exothermic reactions release more energy than they absorb. By contrast, endothermic reactions absorb more energy than they release. Because particles of matter such as atoms, ions, and molecules have kinetic energy, they are continuously moving and colliding with one another. A sufficiently forceful collision can disrupt the movement of valence electrons, causing an existing chemical bond to break or a new one to form. The collision energy needed to break the chemical bonds of the reactants is called the activation energy of the reaction. Catalysts are chemical compounds that speed up chemical reactions by lowering the activation energy needed for a reaction to occur. A catalyst does not alter the difference in potential energy between the reactants and the products. Rather, it lowers the amount of energy needed to start the reaction. After a chemical reaction takes place, the atoms of the reactants are rearranged to yield products with new chemical properties. When two or more atoms, ions, or molecules combine to form new and larger molecules, the processes are called synthesis reactions. All the synthesis reactions that occur in your body are collectively referred to as anabolism. Decomposition reactions split up large molecules into smaller atoms, ions, or molecules. The decomposition reactions that occur in your body are collectively referred to as catabolism. Many reactions in the body are exchange reactions. They consist of both synthesis and decomposition reactions. Some chemical reactions proceed in only one direction, from reactants to products as previously indicated by the single arrows. Other chemical reactions may be reversible. In a reversible reaction, the products can revert to the original reactants. A reversible reaction is indicated by two half arrows pointing in opposite directions. Thank you for watching this video. Remember to like, share, and subscribe to my YouTube channel for more contents.